Hi, I'm Murray Bennett, and this is a pre-recorded presentation for the 2021 meeting of the Australasian Mathematical Psychology Conference. I'll be talking about the cognitive workload and performance of individuals working in competitive and collaborative teams. I'd like to start by thanking Callum McGoldrick for his help with data collection and analysis, and also thanks to Army Idels for his work on the project. Generally, we use teams so that we can get a job done faster, to a higher standard, to achieve things we couldn't on our own, or more importantly, when safety is critical. If we have a task that is too big for one person, teams are beneficial because we can divide the task load between members so one person doesn't have to do everything. Whenever we talk about performance, cognitive load isn't far behind. Any task requires the allocation of cognitive resources to successfully complete. So that might be calculating the appropriate rotation of a bottle of juice, keeping the position of a glass in working memory, and attending to the changing positions of both. If having to do all of this at once becomes too much, that is, the cognitive load is too high, our performance suffers, which might lead to catastrophic errors. Now, when we complete the same task in teams, the additional team members can be thought of as additional resources. We have extra hands to help and extra thinking power to think about and execute the task. In the case of filling a glass, we have extra sets of eyes that can help indicate which glasses might need to be filled next, or warn the filler of any incoming or looming errors. This extra help should help reduce the cognitive load, but let's say communication between members is poor. This might be a source of increased cognitive load and further disaster. So teams can be beneficial, but again, the addition of extra components also brings about a potential source of error via the additional load. So naturally, we need to ask, what team environments are best suited to enhance performance and minimize cognitive load? Research has typically examined the cognitive performance of collaborative groups, as this is often the environment with which teams are utilized for safety critical roles. We see that collaborative teams can effectively divide load in visual search using a split screen method and can also benefit from sharing cues between members. However, collaborative decision makers have also been shown not to improve when team members are not of a similar ability, as the better team member is inhibited by having to cover the load of the other team members. Alternatively, competitive groups have also been shown to perform well, where the competitive environment between team members allows the group to quickly reach near optimal outcomes. Other research on competitive teams in visual search have also showed that team members engage in greater between-member monitoring, which can help increase the accuracy of the team, but also at a cost to speed. When measuring group performance, however, we need to consider the statistical facilitation of effect of aggregating performance over multiple individuals. For example, my single guess of the number of jelly beans in this jar will likely not be as good as the average guess from 20 others. Similarly, a team might also perform better via redundancy gain, where the best time of the group comes from the best individual, and there isn't actually any benefit of the group other than having lots of people doing the job together. To help circumvent this issue of group performance measurement, we aim to utilize the workload capacity measure from systems factorial technology. Workload capacity is typically used at the individual level to measure changes in processing efficiency of a system when additional processing units are added. Very generally, and for example, we could compare how fast someone processes a red light on its own, a blue light on its own, and both lights together to determine whether combining the lights results in an improved or reduced system processing. We can utilize this framework to assess group performance by conceptualizing the processing units not as a light, but as members of a group. So in the experiment that I'll describe shortly, we have two players, red and a blue player. Participants complete the experiment separately to gauge individual performance and then together in different group conditions. Using the workload capacity measure, if the group outperforms two individuals working independently and in parallel, then we can say that the group has a facilitatory effect where there is a benefit to having done the task as a group, and the group can be described as having supercapacity. If group performance is worse, then the group has affected some cost on individual performance. and it's limited. If the group performance is as good as 2 individuals working alone, then the group is unlimited, and we could theoretically just keep adding members to the team and we'd get neither better nor worse. In this experiment, we had 2 participants come into the lab to complete the paddle game at a time. The game is a lot like the arcade games Pong or Brick Breaker, where each player needed to control the horizontal movement of a paddle to deflect a set of moving balls. We manipulate the task difficulty or workload by changing the number of balls that are on the screen during each trial. The experiment was split over 3 blocks, where participants completed each block under a different type of group. So they needed to work collaboratively, compete against each other, or they were given separate tasks. Throughout the experiment, we ran a version of the detection response task, where participants needed to respond to a brief visual stimulus every 3 to 5 seconds, which would stay on for 1 second or until both participants had responded. So here's the setup for the collaborative and competitive conditions. The 2 groups were differentiated by instructions at the start of the blocks. So for example, collaborative groups were told to work together to score as high as they could, whereas competitive groups were instructed to try and outscore your opponent. As you can see, players control the paddles and their job is to deflect or hit the balls. This is a high workload condition where there are 9 balls on the screen per player, so this would make 18 balls here. The balls are coloured purple to indicate that both players can hit any of the balls. All the while, we have the detection response task displaying on the side panels as the green light. Here we record response times and the accuracy. We keep track of the hits and the misses, so a hit is each time the player deflects a ball, and a miss is when a ball passes the bottom of the screen, where it will regenerate at the top, so that we have a continuous and dynamic group task. Participants completed 16 trials per block. There are 4 levels of workload going from 1 ball per player to 3 to 6 and then 9, which is the high workload you see here. Next, we have what we call the separate condition, where players are given separate tasks to complete. You'll notice here that instead of purple balls, the colours have been changed to red and blue. Now, in this condition, each player can only hit the balls that match the colour of their paddle. Now, this is programmatically managed such that if the red player wanted to hit a blue ball, they couldn't, as the ball would just pass through the paddle. We use this condition as our measure of individual performance, as the other player and their task shouldn't have any bearing on the performance of the other. Here are the primary results from the paddle game. Now, these are the mean miss rates for each level of difficulty in each group condition. We have player 1 and 2 in red and blue along the top, representing the performance in the separate conditions, and the collaborative and competitive group results are in the purple below. Here, a higher value indicates a poorer outcome, as it means the participant missed more balls. Overall, the miss rate increased as workload increased and was higher for the task-separated conditions compared to the 2 group conditions. There was no difference between the collaborative and competitive groups, which was interesting. Generally speaking, this indicates that groups outperformed individuals, but we've not been able to find a meaningful difference in the performance between the collaborative or competitive groups. Onto the DRT performance. Now, in terms of cognitive load, a slower response time and poorer accuracy generally indicates that a person is under high cognitive load, as they have fewer resources to quickly respond to the light. However, the response times to the DRT in our task did not follow this trend. There seems to be no difference in response time between groups or workload levels, nor does there appear to be a trade-off between the speed and accuracy, as this pattern is consistent also in the accuracy plots in the right. However, the base condition for the separate task appears to have a clearly faster response time and accuracy. We think this might indicate that participants were overloaded very early by the task, because the separate base workload condition is when a participant only has 1 ball to hit. They have 1 blue ball or 1 red ball to manage, and that was their best response times. And then the next workload level up was nearly the worst, or if not the worst. So what's also interesting is that the increased response time during the low load condition compared to the medium and high load conditions. Obviously, this is counter to what we might expect with the relationship between performances and load. We suspect, given that players may have been overloaded quite quickly by the task, that they adopted different performance strategies across the different levels of difficulty. So next we'll take a look at the behavioural properties of participants within trials to dive into that a little more. So along with the hits and the misses and response times, we also collected positional data, the coordinates for both the players and all balls throughout the experiment. This allows us to examine specific player patterns and strategies. Now, these are just examples from a single trial, but we have from left to right, a separate collaborative and competitive low load conditions being recreated. So already you can probably see on the cumulative histograms there that players tended to stick to one side of the screen, particularly in the collaborative conditions in the middle, where they tend to adopt a screen sharing strategy. On the other hand, in the separate condition on the left, players would need to move to all parts of the screen to successfully hit all of their balls. You can also see in the competitive condition on the right, where although players are still tending to their sides, there's certainly a lot more overlap or creeping into the other player's space, which suggests that players are also tracking the position of other players. We then examined this apparent difference in strategies across groups directly across all trials and participants. Now we can see here that when we look at a basic descriptive plot of the range of the screen covered by either player across workload and groups, that players in the separate condition travelled across more of the screen as they were chasing their balls, followed by competitive then collaborative groups. What's interesting here is that the distance travelled by the players peaks in the low load conditions for all group types, where they're likely chasing the balls as much as they can. However, when there are too many balls on the screen in the medium and high load conditions, they restrict their movements. They don't travel as far. They restrict it to a smaller portion of the screen where they can still obtain a reasonable hit rate without having to do as much work. This difference in strategy between low and medium and high load conditions might help to explain the peak in the DRT response times during that low load condition. In terms of specific group strategy, we can see from an examination of the proportion of the trial time that players spent overlapping one another, that collaborative groups rarely crossed onto each other's domain. So low scores here indicate that they didn't overlap each other, whereas this was less so for the competitive group. Finally, to assess the overall performance of individuals within the groups, we've applied our calculation of workload capacity. Here we compare the miss rates during the collaborative and competitive groups against the assumption that both group members completed their work independently and in parallel. We can see that, so here we combine the separate player performances and subtract the team performance from that and compare it to a benchmark score of 0. So we can see that overall the collaborative groups are slightly better than the competitive, but both group conditions exhibit a limited capacity as their scores are below 0, which indicates that although groups outperformed individuals based off their miss rates, however, this outcome here indicates that there is in fact a performance cost applied to the individuals by having completed the task as a group. The poorest performance occurs during the low workload condition, which together with the analysis of workload and player strategy indicates that group work is certainly, less useful, when there is insufficient work to actually share. To conclude, while groups perform better than an individual, our utilisation of SFT and measures of workload capacity indicate that our collaborative and competitive groups were actually poorer than two independently working individuals. Specifically, performance was poorest in the low condition, which indicates that teams weren't doing too well when they didn't have meaningful task separation. There wasn't enough workload to share. Using player behavioural data extracted from their paddle coordinates, we also observed differences in the player strategy across the two conditions. Collaborative groups engaged in a more balanced screen sharing approach, whereas competitive groups were more likely to track or shadow the movements of their counterparts, supporting previous research in visual search, where they see inter-team member monitoring. What's interesting here is that this difference in player strategy had no effect in the overall performance between the two group types, nor on the cognitive workload measures in the DRT, which indicates that certainly for our task, there are some groups where a little bit of healthy competition can be just as good as collaboration.